All right, welcome back to our series on the math behind machine learning. Today we are digging into something really important. Why picking the right cost function isn't just some technical detail. No, it's a huge strategic call that completely defines how your model's going to learn.
So in our last explainer, we learned that a cost function is basically a scorecard for our model. The lower the score, the better it's doing. But that brings up a really good question. If we're just trying to measure how wrong the model is, why are there so many different scorecards?
Well, the answer is that each cost function is a specialized tool. Think of it like a toolbox. Each one is designed for a very specific kind of problem, a specific kind of data, and it actually encourages a specific kind of behavior from our model. Choosing the right one, well, it changes everything.
Okay, so let's start with the most common task in machine learning, regression. That's just a fancy word for predicting a continuous number, like, say, the price of a house. And for that job, there's a go-to default scorecard, mean squared error, or MSE. The idea behind MSE is actually pretty simple. For every single guess our model makes, we figure out the error, the difference between the prediction and the real answer. Then, here's the key, we square that error. And finally, we just average up all those squared errors. That's it.
Now that squaring part, that is where all the action is. It's not just some random mathematical step. It is the secret sauce of MSE, and it has a massive impact on how the model actually learns. Just look at this. If our model's off by 2, the squared error is 4. Okay, but if it's off by 10, the squared error isn't 10, it's not even 20, it skyrockets to 100. This huge out-of-proportion penalty means the model becomes absolutely obsessed with fixing its biggest, most embarrassing mistakes first.
So why is this the default then? Honestly, because it's super convenient and really reliable. Squaring the error creates this perfect, smooth, bowl-shaped curve. And what's great about a bowl shape? It guarantees there's only one single lowest point, a global minimum. This means our optimization algorithm, gradient descent, can just slide right down that curve and find the best solution without ever getting lost or stuck.
But here's the twist. What happens when our data isn't so nice and tidy? Let's see how MSE's biggest strength, that harsh punishment for big errors, can suddenly turn into its greatest weakness. So, picture this. You've got a model that's doing a fantastic job predicting house prices. The trend line looks great. Now, let's add one single data point that's a total outlier, like a $10 million mansion in the neighborhood of regular modest homes. Because MSE absolutely hates that massive squared error. It will literally drag its entire prediction line way off course, making it worse for all the other normal houses, just to get a little closer to that one weird outlier.
And this is the core of the problem. The model's behavior just gets completely skewed. It's no longer representing the real trend in the data because it's getting bullied by that single crazy data point.
So, if our data has outliers and we don't want them to completely take over the model, we clearly need a different scorecard. Let's check out a more robust alternative.
And this brings us to mean absolute error, or MAE. It takes a much more, level-headed approach. Instead of squaring the error, it just takes the absolute value. Simple as that.
This comparison right here is key to understanding the difference. With MSE, the penalty grows exponentially. It just explodes. But with MAE, the penalty is linear. An error of 10 is punished exactly 5 times more than an error of 2. There's no dramatic, outsized punishment for being way off.
And the result of that linear penalty? Well, the model becomes way more stable and robust. That one expensive mansion from our example, it doesn't have the power to drag the whole line off course anymore. MAE just sees it as one error among many, not some 5-alarm fire it has to put out.
This all sounds great, right? I mean, if MAE is so much better at handling outliers, why on earth isn't it the default? Well, like with everything in machine learning, there's always a trade-off.
The problem is, you guessed it, a mathematical one. The absolute value function isn't a smooth bowl like MSE. It has this sharp V-shaped point right at the bottom. And at that exact point, the slope is undefined, which means our gradient descent algorithm can kind of get confused and struggle to know precisely when it's hit rock bottom.
Okay, so we've looked at 2 ways to handle errors when we're predicting numbers. But what if we're not predicting a value at all? What if, instead, we're trying to choose a category, like classifying an image as a cat or a dog? Just measuring distance doesn't really make sense here. This is a whole new ballgame, and it needs a completely new kind of scorecard.
For this, we use something called cross-entropy loss. It's designed specifically for classification models that spit out probabilities. So instead of measuring a numerical distance, it measures how different the model's predicted probability is from the actual truth.
What makes cross-entropy the right tool for the job is that it's built from the ground up on probability theory. It works perfectly with models like logistic regression or neural networks that give us probabilities as their output. And, just like MSC, for many of these models, it creates a nice, convex error surface, so we're guaranteed to find the single best solution. The main idea here is that it's not about being close to the answer, it's about being confident in the right answer.
Okay, let's bring this all back together now. Choosing a cost function isn't just a mathematical detail you plug in. It's about really deeply understanding your data and aligning your model's training process with the story that your data is trying to tell you.
This table pretty much sums up the core trade-offs we've been talking about. You've got MSE, the smooth, reliable default for clean regression problems. Then there's MAE, the robust, outlier-resistant alternative you call in when your data gets a little messy. And finally, you have cross-entropy, the probability expert, the specialist for all your classification tasks.
And ultimately, this is what I want you to take away. Your cost function is your training strategy. So before you pick one, you have to interrogate your data. Ask it questions. Does it have outliers? Are you predicting a number or a category? Answering these questions first is absolutely the key to picking the right tool for the job. And join us next time as we dive into a little bit of terminology cleanup. We're going to explore the subtle but really important difference between a loss function and a cost function. Thanks so much for watching.